Okay, so hi, I'm Madeline Abbott. I'm a current PhD student in the department, and I'm just going to talk to you briefly about one of the projects. That's a dissertation project that I'm working on. And so this project is titled A Continuous Time Dynamic Factor Model for Intensive Longitudinal Data Arising from Mobile Health Studies. And so this is work that's co-advised by my dissertation advisors, Jeremy Taylor and Walter Dempsey. And so this work is motivated by a specific mobile health or mHealth data set. And this data was collected by a team of researchers here at Michigan and then also at the University of Utah, including Billy Nahum-Shani, who's my GSRA advisor, and then Joe Lam and Dave Wetter, who are at the University of Utah. And so this is a longitudinal cohort study of smoking cessation among 218 African American smokers who are attempting to quit. And so everybody who enrolls in the study is a current smoker, and they quit on what we're calling day 0. And then they're followed for 10 days. And then during each of these 10 days, they're prompted to respond to up to 4 EMAs per day. And so here EMA stands for ecological momentary assessment, and is just a common method for collecting data in the mobile health setting. In this specific study, these EMAs take the form of surveys that are sent to people's smartphones. And so they just contain a bunch of different questions. So in this study, we're interested in a subset of questions that assess these individuals, their mood over time. And so they're asked a set of about 20 questions that aim to capture how intensely they're feeling a bunch of different emotions. So they're asked, right now, I feel angry, bored, happy, sad. There are 20 or so of these emotions. And they respond on a scale from strongly agree to strongly disagree. So as a result of this, we get information on multiple longitudinal outcomes. So here it's 18 different emotions that are measured up to 4 times per day across 10 days. And so this is what we want to model. In this plot, I'm showing you one subject's response over time. So here on the x-axis, we have days since quit, 0 to 10. And on the y-axis, that corresponds to how intensely this person reports feeling these 18 different emotions. So a positive number means they more strongly agree with currently feeling these emotions, and a negative number means they more strongly disagree. And so I plotted the 9 positive emotions on the top, and then the 9 negative emotions on the bottom. And so in this plot, each point represents an EMA and their set of responses to the questions in that EMA. And then I've just highlighted a random 3 of each to make it easier to see what's going on. But I guess there are 2 important patterns to take away. First is related to the correlation. So you can see positive emotions are pretty strongly correlated with each other. They all tend to move together, and then the same goes for negative emotions. But then if you look across positive and negative emotions, you can see when positive emotions go up, like around, I don't know, day 1 or so, negative emotions tend to dip. And so there's also correlation, negative correlation across the 2 types of emotions that we want to capture. And then the second pattern to take away is the rapid variation in the emotions over time. And so they tend to jump up and jump down. And so that's also something we want to capture in our model. So this brings us to the motivating question. Can we use the data collected via EMA from current smokers attempting to quit to model changes in their emotions over time? But there are a couple statistical challenges that we want to take into account when we're doing this. And so the first is that we have intensive longitudinal data. So we have 18 different emotions that are measured up to 4 times per day, which is a lot of information if we wanted to directly model all those 18 outcomes at once. So instead, we summarize here the observed longitudinal outcomes, which are the emotions, as lower dimensional latent factors. So in this case, you could think of summarizing the observed 18 emotions as 2 unobservable latent factors that represent positive mood and negative mood. The second challenge is that we have unbalanced data. So rather than having the measurements taken on a grid, which would be balanced data, the measurements aren't uniformly spaced, since the EMAs are sent randomly throughout the day. And so this restricts the class of models that we can use, since we can't just assume that time is a grid. And so instead, we model the change in time, or change over time, of the latent factors using a continuous time stochastic process. And then the third challenge is that we have a highly variable outcome. So if you remember from earlier, the emotions, those measurements go up and down pretty quickly. And so that's some sort of change we want to account for in our model. And so to do that, we use a specific model, an Ornstein-Uhlenbeck stochastic process that is able to capture those abrupt changes. So our proposed approach is here. It consists of two models, the measurement submodel and the structural submodel. And then I'll go through this diagram in more detail on the next slides. But the first model is the measurement submodel, specifically what's called the dynamic factor model. And the purpose of this model is to summarize the observed longitudinal outcomes, so the emotions, as latent factors that vary over time, where these latent factors are like positive mood or negative mood, which here we're calling positive affect and negative affect. So in this diagram, the 18 emotions, those are represented with the Y's. So here yi, 1 of t would be one emotion measured for subject I at time t. And then we want to summarize those as here we have two latent factors that represent positive and negative affect. But you could think of a different setting where you might just want one latent factor or you might want three. And so then the specific model is given here. So for subject I at time t, we assume yi of t, which is the vector of observed longitudinal outcomes, is equal to lambda times eta I of t, which is the latent factors, plus ui plus epsilon I of t. And so this lambda is the loadings matrix, which in like standard linear regression you could think of as your beta coefficients. And that describes the association between the latent factors, the etas, and the observed outcomes, so the y's. And then because we have repeated measurements across time, we also want to account for that correlation within a subject. And so we include the ui term, which is a random intercept. And then the last term, the epsilon I of t, this represents measurement error, since we might not be measuring the observed longitudinal outcome perfectly. And so just to summarize, the purpose of this model is to model to summarize the observed longitudinal outcomes as lower dimensional latent factors that then vary over time. And so then to model the evolution of those latent factors over time, we use the structural submodel, so specifically the OU stochastic process. And so here I've just simulated data from a bivariate OU process where these two latent factors within the process are negatively correlated. So you could think of them as positive and negative affect. So when one goes up, the other one goes down. And there's also quite a bit of variability in the values of those processes over time, which is something that we wanted to capture. And so then down here, I've been giving you the stochastic differential equation definition of this process, which I guess looks a bit scary, but the main point is that we just want to model the change in the latent variables, which is this d eta term, equal to some function of the current value of the latent variables, which is the second eta I term, plus some term for noise. And so there are two matrices of parameters that we need to estimate, the theta matrix and the sigma matrix. And so this is just how we model the change in those latent variables over time. And then there were a couple reasons that we chose this specific model. First, it assumes continuous time, so we don't have to worry if our measurements aren't taken on a grid. Second, it's autocorrelated, meaning that measurements taken more closely together in time will have a higher correlation than measurements taken far apart in time, which makes sense in this setting. Third, it's mean reverting. So here the mean we're assuming is 0. And this means that over time the process will always come back towards the mean eventually, rather than going off to infinity, which also makes sense in this setting. And then the last property, this process also has the Markov property, which means that the current value only depends on the previous value and nothing before that, which is nice for simplifying things later when we try to fit this model. So just to summarize, we proposed a dynamic factor model that consists of two parts, a measurement submodel, which we use to summarize the observed longitudinal motions as lower dimensional latent factors, and then a structural submodel, which models the change in those latent factors over time. So then to fit the model, we take a maximum likelihood approach and use an iterative block coordinate descent algorithm where we aim to estimate 4 or 5 matrices of parameters given the current data that we have. And so 3 of those matrices of parameters, the lambda, the sigma u, and the sigma epsilon, those belong to the measurement submodel. And then we have the matrices theta and sigma, those belong to the structural submodel. And so our goal is to estimate those parameters given the current data y. And then we also want estimates of uncertainty. So to get standard error estimates, we use Fisher information, which is a a pretty common approach to doing this. And so then we can apply our model to the mobile health data that we looked at before. So in this specific example, we have 18 longitudinal outcomes. Those are the emotions that measure the intensity of 9 positive emotions and 9 negative emotions. And then we use our model to summarize these 18 observed emotions as 2 latent factors that represent positive affect and negative affect. And in this, we just assume that we know that the 9 positive emotions are a summary measure just for positive affect, and the 9 negative emotions are a summary measure just for negative affect. And so we don't assume that the negative emotions are somehow related to positive affect, and the observed positive emotions are somehow related to negative affect. So then in this plot, I'm giving you point estimates and 95% confidence intervals for the elements of the loadings matrix, that lambda. And so these describe the association between the observed longitudinal variable, so the emotion, and the underlying latent variable, so positive or negative affect. And then, so just to highlight a couple points, so happy, joyful, and enthusiastic, those are the 3 emotions that are most strongly associated with positive affect, and then sad and irritable are the observed emotions that are most strongly associated with negative affect. And then in this next plot, I'm giving you estimates of the variance components for the random intercept. And so this is telling us, how much between subject variation is there in these observed emotions. And so you can see there's a lot of between subject variation in like baseline levels of proud and lonely. And so that sort of makes sense, since those might be emotions that are a little bit more stable. Since the study is only 10 days long, they probably don't change that much. Whereas happy and calm, disgusted and angry, those might be emotions that fluctuate a bit more over time. And then in this last plot, this plot is showing you the estimated correlation of those latent factors, positive and negative affect, when they're measured across various gaps of time. So the x-axis here is gaps of time, and then the y-axis is estimate of correlation. So looking at the blue and orange line on the bottom, this is telling you what the correlation between positive and negative affect is when they're measured across various amounts of time. So I guess if they're measured at the same time, this is telling us there's a negative correlation of about 0.8 between those 2 latent factors, which is a pretty strong negative correlation. But then this correlation decays fairly slowly across time. So still about 2 days out, 50 hours-ish, the correlation is maybe negative 0.3. And then the top 2 lines, the blue and the yellow one, those are showing you the correlation between measurements of positive affect with positive affect and negative affect with negative affect. And so it makes sense, they're positively correlated, but this correlation also decays over time. So then just to summarize, in this work we proposed a dynamic factor model which summarizes multivariate observed longitudinal outcomes, so the emotions, as lower dimensional latent factors, which here were positive and negative affect. And then we modeled the temporal evolution of those latent factors in continuous time. And then this last point here, I didn't really talk about much at all, but there were a lot of tricks that we had to use to get our model, or I guess the estimation approach, to run fast enough to actually make it feasible to fit this model, which is where a large chunk of the work went. And then the last point here is just future work. So in this work, we only had the observed longitudinal outcome. We didn't have baseline covariates like age or gender or something like that. And so that's something we could include in the future if we wanted to see if the patterns that we saw differed by age or gender, for example. And then the last point, so these data were originally from a smoking cessation study. So everybody has quit. And then we know over time when they do smoke cigarettes, so we might want to link their level of positive and negative affect with the risk of them smoking a cigarette, for example. And so that would be an interesting next step. And then finally, I just have some references and funding acknowledgements. But I'm happy to take any questions if you have them. Yeah.
To what extent does intervention itself cause some sort of... You asked about your emotional state.
Yeah, that's a good question. Yeah, I'm not sure if, like, just based on these data, we would be able to know that. Yeah, I guess in this study, people are paid each time they fill out one of those surveys, so that could also definitely be a factor. I guess the hope is that since the EMAs are sent at random points throughout the day, you're at least like the measurement is somewhat random, and so you're not always measuring people's emotions, like when they wake up right away in the morning when, I don't know, maybe they're not feeling as good as they would in a couple hours. But yeah, I'm not sure about like the actual measurement itself and how that would impact the outcome. Yeah.
I'm just kind of curious about like where you are in the research project, kind of like how many years or how much time it's taken, where you, I know you kind of talked about places that you want to go, but what is still left to cover, just kind of, yeah, how you've ended up with this.
Yeah, no, that's a good question. Yeah, so this is my 5th year here. So I did 2 years in the master's, and then this is my 3rd year in the PhD program. And so this is the first chapter of my dissertation, which I guess I started my 1st year in the PhD program, I think. But yeah, so I guess this is just the first chapter, which I guess maybe I'm like almost 2 years into. And so then the 2nd chapter of my dissertation, I guess the goal is to link this model with a time to event outcome. So time to cigarette, for example. And then in the 3rd chapter of my dissertation, there's another study which is fairly similar to this, but it has an intervention in it. And so the goal is that it's like prompts sent to people's smartphones. And I guess the aim is that sending people prompts to remind them why they've quit smoking will help them, I guess, succeed in quitting smoking. And so then the goal of the 3rd chapter is sort of to estimate treatment effects of those prompts. And so I haven't started on that one, and I'm sort of part way through the linking this with the time to event outcome. Yeah. Yeah. Oh, sorry.
I'm Sam. Great presentation. You said that you started this program.
Yeah, no, that was my original goal. Yeah, so I worked with Jeremy during the master's, and so enjoyed that, and so I guess kept working with him, and then added Walter as a co-advisor. Yeah. Yeah.
The original data, or was it just data that was already out there?
Yeah, so yeah, I wasn't involved in data collection at all. My GSRA is with Billy Nahumjani, who was involved in the study, and she's a professor at ISR. And so it was like through her, working with her, that I was able to use this data. But yeah, so no, this data was, it was collected recently, but the collection was finished before I got involved in this project. Yeah. Okay, if there are no other questions, thank you.